All right. Hello, everybody. Welcome to this month's episode of Rocky World's Discussions. Today we have Megan Newcombe from the University of Maryland to give a talk about efficient degassing of early formed planetesimals, water delivery to Earth via unmelted materials. And before we start with Megan's talk, just a short for those of you who may be here the first time or watch this as a recording later on. So we usually start with a short introduction, which I'm doing at the moment. Then we have a 30 to 40 minute talk by a given speaker. And then the idea of these Rocky Worlds discussions is actually really to provide an open platform across the world for discussion. And so that we have an extended time frame for discussion. So which is why I also encourage you to really, during the talk, to think about how the talk of the day or the discussion that is presented by the speaker potentially connects with your talk and ask engaging questions afterwards. You can also discuss amongst yourself. So we try to usually transition from a Q&A with the speaker to more open discussion. And with this, I want to stop here now. The only thing is please use your full name and later on when you ask a question, please display your video if at all possible. And now I want to stop talking and I will stop sharing my screen. And hand over to Megan. Please take it away.
Well, thank you so much, Tim, for the invitation. And thanks for all of the organizers of this Rocky Worlds discussion series. I think it's such a great community building effort, and I'm happy to participate in this discussion. So I'm going to be talking today about some work we've been doing to kind of constrain the role of thermal metamorphism and melting on controlling the water budget of materials that could have accreted to Earth. And the main motivating question driving this work is, where did Earth's water come from? So I'm showing here this artist's rendition of the early solar system. You can see the disk of hydrogen-rich nebula gas. And in fact, this disk of gas has been proposed as a potential source of Earth's water via nebular ingassing, perhaps by adhesion of hydrogen onto the surface of mineral grains or by ingassing into magma oceans. But there are other water-rich materials in this picture. We have the icy-rich comets, and we also have water ice and organics that are accreted to these rocky bodies in the middle here that are becoming the planetesimals and planetary embryos that collided and accreted to form the Earth. So we can sample those rocky bodies via our meteorite record. It's not a complete sample of the kinds of materials that were available to accrete the Earth, but it's the best we've got. So we classify our meteorites in various ways, one of which depends on the amount of kind of thermal processing, aqueous alteration, and melting degree that they've experienced. So the chondrites, they can be thought of as cosmic sediments. These are materials that accreted directly from the solar nebula. You can see the little chondrules in here, and a watery rich matrix material holding them together. These have experienced some amount of thermal and aqueous alteration that is required to lithify these rocks and help them to survive their fall to the Earth, but they have not experienced melting. If we move up a degree of heating, we actually reach the point at which these materials begin to melt, and these form the primitive achondrite meteorites. So these come from parent bodies that experience low degrees of partial melting, but they likely didn't experience a global magma ocean, and they didn't experience extensive segregation of components into a crust, a mantle, and a core. So their bulk compositions are typically similar to the chondrites that were their precursors. Then finally, we have the achondrites. These experienced extensive melting and also metal silicate segregation. And they likely also had magma oceans. So something very exciting happened in the meteorite community in around 2011, when Warren published this paper that said that all known meteorites are segregated in terms of their isotopic compositions into these two groups, that we refer to as the dichotomy. And so I'm showing here just two isotopic systems in which this has been shown. There's on the y-axis, we have Cap17 oxygen, and on the x-axis, we have epsilon 54 chromium. And you can see that there's a pig field here, which defines our non-carbonaceous materials. And in this field, we have the terrestrial planets, and we have most of our achondrite parent bodies, such as the anhydrous and the ureilites. And then we also have a few chondrite groups. We have the ordinary chondrites, we have the enstatite chondrites, which are isotopically very similar to the Earth, and we have the achondrites. And then in the blue field here, we have mostly our carbonaceous chondrites, along with a few rare achondrites. So how does this relate to volatiles? Well, we think that this dichotomy originated by the spatial segregation of these materials in the disk, potentially separated by the growth of Jupiter. And so the carbonaceous chondrite reservoir, we think, formed in the outer solar system, where we have the water-rich carbonaceous chondrites. And then we think that the non-carbonaceous reservoir formed in the inner solar system. And somewhere along this system, we have what's called the snow line, which is the distance beyond which water is stable as ice. And if a material accretes in the presence of ice crystals, then it can accrete very water-rich. But if it forms within the snow line, in this warmer region of the inner solar system, then the thinking is that it doesn't accrete as much water. We do have some water-bearing non-carbonaceous materials, such as the ordinary chondrites. And I know that the position of this snow line is something that is highly debated, and I'd love to hear your thoughts about that during the discussion. But in general, this picture gives us a bit of a puzzle for how Earth got its water, because if the Earth did form within the snow line, then it would have formed from relatively dry material. But we have all of these surface oceans. And so it's been a bit of a puzzle for us to work out where these oceans came from. And one popular theory says that material from the outer solar system, which is very water-rich, from this carbonaceous chondrite reservoir, could have been scattered into the inner solar system at around 4 million years after the solar system formed, potentially by the migration of Jupiter inwards and then outwards in a model that's called the Grand Tack. And so scattering this water-rich material inwards so it could accrete onto the Earth is a potentially good way of explaining how Earth became quite a water-rich system, even though it formed in the warm inner solar system. And in fact, this model fits relatively well with isotopic constraints. So I'm showing here analyses of 15/14 nitrogen against the DH ratio of water in various different rocky materials. So we have the Earth in green here at 0, 0. And you can see that the Earth's isotopic composition falls in the same region as the carbonaceous chondrites. And so Earth's water matches carbonaceous chondrite material pretty well. Also shown on here, we have nebular hydrogen, which is very light in these isotopes. It contains less deuterium and heavy nitrogen. And we have the comets up here, which have a lot more deuterium and heavy nitrogen. And it's tempting to think, well, maybe we can mix in some nebular hydrogen and some cometary material and form a reservoir that looks like the Earth. But what's shown here with these dashed colored lines are mixing lines on this plot, which you can see are very strongly curved. So in fact, mixing cometary and nebular hydrogen completely bypasses the Earth. So the simplest explanation here is that carbonaceous chondrite material was mixed into the Earth and can explain Earth's water budget. And in fact, this works pretty well as well for relative abundances of various volatiles, not just water. So this is showing the abundance of volatile elements divided by the CI chondrite composition. And you can, we find that addition of around 2 to 4% carbonaceous chondrite material to a volatile depleted proto-Earth does a very good job of explaining Earth's volatile budget, with a couple of notable exceptions. Xenon is very low on this diagram, which we think is probably due to progressive loss of xenon to space, and nitrogen is also low. That could also be nitrogen going into the core, nitrogen being lost to space, or possibly just an underestimation of the terrestrial nitrogen budget. So does this mean we can go home? Everything so far seems to work pretty well. Well, and there are various other theories for how Earth got its water that we need to consider. And so I said earlier that Earth is isotopically very similar to the enstatite chondrites. And there are certain inner solar system materials, the ordinary, the enstatite, and the achondrites, that do contain volatiles. And so what we need to consider is that Earth didn't need this delivery of water from the outer solar system. And perhaps it could have obtained its volatile budget from materials that were the primary accretionary building blocks. So in order to, this theory has been supported by recent work that has characterized the water content of enstatite chondrite meteorites. This Piani et al. 2020 study performed bulk measurements of enstatite chondrites and also their differentiated counterparts, the aurites, and they found that the water budget of these enstatite chondrites and the aurites were actually sufficient to explain Earth's entire volatile budget. And I'm particularly interested in the position of the aurites on this plot. I don't know if you can see my mouse, so I'm just gonna.
We see your mouse.
You see it, okay. Okay, thanks. And so the aurites here are also, they're just as elevated in water as the enstatite chondrites. And so this kind of suggests that even though these enstatite chondrites have gone through thermal metamorphism and then melting and differentiation in the aurite parent body, and that potentially differentiation and melting are not leading to water loss, which I found pretty surprising. And so I wanted to think more about whether water and other volatiles are retained during melting and thermal metamorphism. And this will kind of answer whether we need late delivery of carbonaceous chondrite material to explain Earth's water budget, or whether we can simply accrete and retain materials during Earth's primary accretion. So to answer this question, I've looked at volatiles in two different sets of meteorites that I'll be talking about today. The first one is rare achondrites that accreted in the outer solar system in the water-rich carbonaceous chondrite material in region. So we know because these formed in the carbonaceous region that they accreted water ice. They started their lives water-rich, but they have melted. And so we can use these meteorites to answer whether they are able to retain their volatiles during melting and differentiation. And then secondly, we'll look at the primitive achondrites, an example of these being the ureilites. So these meteorites partially melted, but we think they never had a global magma ocean. So we can then answer the question of whether a global magma ocean is required to outgas volatiles, or whether the volatiles could have been lost prior to that during thermal metamorphism. So I'm going to start off with the rare achondrites that accreted in the water-rich carbonaceous chondrite region. So a lot of these achondrites that have, they're identified as having formed in this carbonaceous region by their isotopic composition. For example, their Cap17 oxygen and epsilon 54 chromium again. Those values put them in the carbonaceous chondrite field, yet they are achondrites. They have experienced melting and differentiation. These are quite rare samples, and a lot of them have been found only recently. Quite a lot of them have found in Morocco. And so they come with very little context, unfortunately, because they're so rare. We think that they came from probably quite small parent bodies, likely planetesimals. And so we've analyzed a set of these ungrouped achondrites from both the carbonaceous field and the non-carbonaceous field. So we think that these ones on the left formed from 3 different parent bodies in the outer solar system, and the ones on the right formed from 2 different parent bodies in the inner solar system. So this is hopefully a good test of, we think that their initial conditions were quite different in terms of their water budget. So we're going to see what the effect of melting and differentiation was on their final water budget. So to do this, we've measured volatiles in minerals and melt inclusions by secondary ion mass spectrometry. This is the instrument we use, the nanosims, at the Carnegie Earth and Planets Lab. And on the right, I'm showing a calibration curve from one of the studies that we've done. Feel free to ask me about this technique in the discussion. So what's going to be really important for us is how we quantify our blank and really working on getting our detection limit as low as possible. And so we do this by analyzing samples that we know have 0 or very, very little water. And I actually analyzed 2 such materials during these sessions. One is a synthetic forsterite crystal, which we really think contains 0 parts per million of water. And the other is a silica glass, which we think contains 2 parts per million of water. And because I can measure this separation between synthetic forsterite and suprasil, which has 2 parts per million of water, I can be pretty confident of my ability to measure these very, very low water concentrations. And my blank here, you can see I'm measuring just over 1 part per million of water in synthetic forsterite. So that's an assessment of the blank in this first session here. I'm overlaying now my analyses of the meteorites. And so in the blue labels, these are the carbonaceous achondrites. And in the brown labels, these are the non-carbonaceous achondrites. And you can see that I've analyzed various phases, various meteorites. Every single phase and every single meteorite we analyzed contained less water than suprasil glass, so less than 2 parts per million of water. Furthermore, I can blank correct the data, which allows me to put a very conservative upper bound of 2 parts per million of water in all of the meteorite nominally anhydrous minerals. In fact, these are among the driest measurements ever, I think. And so these parent bodies appear to be drier than nominally anhydrous minerals from the moon, and also nominally anhydrous minerals from other achondrite groups, the anhydrites and the eucrates. We can use constant partition coefficients between water partitioning in minerals and coexisting equilibrium melts to estimate how much water would have been in the equilibrium melt that these minerals crystallized from. So because water is very incompatible and doesn't dissolve in big quantities in these minerals, a lot of these values here are very conservative upper bounds on the amount of water that would have been in the coexisting melt. One particularly good constraint is from melt inclusions that we found in this meteorite, Northwest Africa 6962. So in this sample, we were able to find actual parcels of melt, which give us a direct constraint on the composition of melt from that parent body. And if we consider how that parent body formed, we think that this meteorite formed by crystallization of around a 30% melt of chondritic precursor material. And if that's the case, then we think that the parent body it formed in contained 3 to 13 parts per million of water. And so this is using an equilibrium melting model, and we can relate the water in a partial melt to the water in the bulk parent body that it formed from. So our results in general indicate that melted material is very dry, regardless of whether it formed in the outer solar system and accreted a bunch of ice, or the inner solar system. And a corollary of this result is that some of this material in the carbonaceous chondrite reservoir was actually melted and therefore dry. And so one of the results of our study is that we can't just use like the Cap17 oxygen or epsilon 54 chromium signal of being carbonaceous. We can't just kind of mass balance that addition of that material to the Earth and say that all of that material was volatile rich, because in fact, a lot of this carbonaceous chondrite reservoir, based on the existence of a lot of iron meteorites with a carbonaceous signature, was likely melted and therefore very water depleted. So I want to think a bit about why these melted meteorites might be so dry. And there are various mechanisms we can look to for drying out chondritic precursor material. So a big one is for very early formed bodies, and we have the decay of 26 aluminum, which bakes surface material from within. We also have a lot of impacts happening during the early solar system. So flash melting during these impacts can also cause these superficial magma oceans that can degas volatiles into space. And we think that only large embryos are capable of retaining our water in an atmosphere and not entirely drying out. So we wanted to ask the question of how large does a planetary embryo need to be to retain its hydrogen during thermal metamorphism or melting? We're not entirely sure at this point at what stage or at what temperature the volatiles are being lost. So it could have been during thermal metamorphism, which we're assuming for simplicity happened at 500 degrees C. It could also have been during the magma ocean stage, which we assume for simplicity happened around 1500 degrees C. And so we've done a very simplistic calculation here it equates the thermal velocity of the vapor molecules to their escape velocity. And what this does is it tells us the minimum radius of a planetesimal that is required to keep molecules of water or methane or hydrogen on the surface of that planetary embryo. So for thermal metamorphism, meteorite outgassing experiments have shown that if you heat up ordinary chondrite or enstatite chondrite material, the dominant H-bearing species outgassed is methane. Whereas if you heat up carbonaceous chondrite material, the dominant H-bearing species outgassed is water. So these are the two species that we've considered for this simple model. And what we find is that you need around 1,000 kilometers radius to be able to retain water and methane. If instead we lose our water during magma ocean degassing at around 1500 degrees C, then the species that are most important for magma ocean outgassing are molecular hydrogen under low oxygen fugacity conditions, that's lower than around iron wüstite, or molecular water at high oxygen fugacity conditions higher than iron wüstite. And the results of this calculation suggest that if you have a low oxygen fugacity system, you need around 3,000 kilometers radius to retain that molecular hydrogen. That's around the size of Mars. And if you have a high oxygen fugacity system, and then you need around 1,000 kilometer radius to retain molecular water. So overall, our results are suggesting that water is very efficiently lost during melting and thermal metamorphism on planetesimals, but you can probably see from the previous calculation that it's really important to understand when the water is being lost. Is it during initial thermal metamorphism, or is it during the magma ocean stage? Because that is going to have implications about how big the planetary embryo needs to be to retain its hydrogen. And so we wanted to think next about when this water was being lost by looking at a different set of meteorites. We wanted to look at a set of meteorites that we don't think experienced a global magma ocean. And by looking at that type of meteorite, we can answer the question of whether a global magma ocean is required to efficiently outgas the water. So the set of meteorites we chose were the ureilites. Now, we chose the ureilites because they exhibit a very wide range of cap-17 oxygen. Now, cap-17 oxygen variations in this are mass independent, and they're thought to be inherited from heterogeneous nebular materials. And so the fact that, in contrast to a lot of these parent bodies that have a very narrow range of cap-17 oxygen, the fact that the ureilites preserve this huge range here suggests that they accreted heterogeneous nebular materials that then were unable to mix fully. And so because a global magma ocean would very efficiently mix all of this heterogeneity up and reduce it to one of these narrow bars, it's thought that the ureilites cannot have experienced a global magma ocean. Another interesting thing about the ureilites is that they have a very high carbon content, and in fact, they have a very similar carbon to nitrogen ratio to the Earth. And because of this, they have been proposed by a couple of studies in the literature to be a potential source of terrestrial volatiles. But notably on this plot, we have no hydrogen data for these meteorites. And so we thought it was going to be quite important to characterize the hydrogen budget of the ureilites. And this work has been done by my very talented graduate student, Liam Peterson, who successfully wrote a NASA finance proposal to support this work. So yeah, thank you, Liam. And Liam analyzed volatiles in a huge suite of ureilites, including the main group ureilites, which represent the mantle lithology, and also this kind of rare Alma meteorite, which is thought to represent a rare sample of the crust of the ureilite parent body. You'll notice in this picture that we have a close-up image of one of the pyroxene crystals from Alma, and it contains melt inclusions. So this was a very exciting sample for us because we love to get these pristine samples of melt. It's much easier to get an upper bound on the water content of these systems from a sample of melt than from using the nominally anhydrous minerals. So Liam analyzed the melt inclusions in Alma and found that they contain around 50 to a couple of 100 parts per million water. He thinks that the enrichment on this diagram that we're seeing as a function of the diameter of the melt inclusions is actually a function of post-entrapment crystallization inside the melt inclusions, which enriches their water concentration from what their initial trapped value was. And so we think actually the best value for Alma is this 50 ppm, which is the same as the water content of the interstitial glass. And then for the mantle, he measured clinopyroxenes that have a maximum of around 6 parts per million of water in them. So this is a nice system because we have samples of both the restite of melting and also the liquid fraction of melting. So by putting these two samples together, we can get some nice constraints on what the bulk parent body water budget might have been. So Liam did several models of varying complexity in order to get at this question of how much water was in the ureilite parent body. And I don't have time right now, but we can return to this in the discussion if you like, to go through all of this. But we think that the best constraints come from this aggregate melt of his dynamic melting model and also a simple mass balance approach. And the range obtained by those two approaches is 3 to 20 parts per million of water in the bulk parent body. So if we assume a precursor composition for the ureilite parent body that's similar to sea achondrites, then Liam's results suggest that the main group ureilites lost more than 99.9% of their accretionary water. So this is a diagram showing the water content of the parent body ratioed to the water content of sea achondrite, and the ureilites are down here at 10 to the minus 4. So this result suggests to us that a global magma ocean is not required to efficiently outgas water. We know that the ureilites didn't have a global magma ocean, and evidence suggests that they've very efficiently dried out. So this moves back in time the point at which we think this water is being lost, and suggest that it might be during thermal metamorphism, or perhaps, local melting and magma oceans, but certainly a global magma ocean is not required. So I wanted to return briefly to these very high, relatively high water contents of the aurites, which were suggestive that water wasn't being lost from the enstatite chondrites during melting and differentiation. So Liam and I were pretty puzzled by this, and so Liam did an extensive survey of aurites, and so he's analyzed aurites by nanosims, by secondary ion mass spectrometry, and these are in situ analyses. So the spot size is 10 microns across on lots of individual grains from a suite of aurites that ranges in their relative weathering and shock stage. And he finds that all of these minerals are actually very, very dry. There's an upper boundary of around 10 parts per million of water in the enstatite in the aurites. So this new data revises down the aurite parent body water content by several orders of magnitude compared to the bulk measurements that were presented by the Piani study. And we think that effectively this is a result of the fact that bulk measurements it's so difficult to remove terrestrial contamination. And so we think that those measurements may have been affected by a small amount of terrestrial contamination. So to summarize the results of our work, we've analyzed volatiles in carbonaceous and non-carbonaceous achondrites and ureilites, which are primitive achondrites. These samples represent the earliest stages of planetary accretion and melting, and they're really dry. So we think that degassing of melted material during heating by 26 aluminum or during impact events is very efficient. And the ureilites, the fact that the ureilites have also efficiently dried out shows that a global magma ocean is not required for this process. So we think the water was likely delivered to Earth via unmelted material. And a corollary of this is that a carbonaceous chondrite signature does not necessarily indicate water-rich material, because part of that reservoir was melted and therefore likely dry. So to seed the discussion, I wanted to just think about the conditions under which planetesimals could keep their water. And so I am drawing heavily on work done by the modeling community and a lot of the expertise in this room. So one way in which planetesimals can keep their water is results of thermal models by Tim Lichtenberg and others suggest that if they accrete very early but remain small, like less than 20 kilometers, then they won't undergo melting. And also if they accrete late after a lot of this 26 aluminum has decayed, then they also won't melt regardless of their size. So I think models that consider these very small parent bodies and the fluxes of bodies that have water contents that depend on their size and their time of formation are a really exciting avenue. And then there are other models that have been put out that could produce water-rich planetesimals. So one option for doing this is instantaneous accretion models. So if you take very small bodies that don't accumulate enough 26 aluminum to undergo melting, and you combine them into embryos that are Mars-sized instantly on a time scale that is much faster than the decay of 26 aluminum, then the rate of accretion is much higher than the rate of differentiation. You can reach that critical size that's needed to retain your water vapor before you do the melting and drying stage. So that's another way that you could retain water. And then finally, I really like this idea of protracted accretion or these cold porous lid models. So thinking about planetesimals not just as a homogeneous blob, but as things that can be quite heterogeneous in both their extent of melting and their water contents. So the idea here is This is a model by Sturz et al. From 2022, showing that if you have protracted accretion, so building, like constantly delivering chondritic material over a relatively long period of time, then you can melt and differentiate the interior of the planetesimal, but you can retain an unmelted crust. And that unmelted crust could be water rich, whereas the melted interior is likely dry. And then similarly, this cold porous lid model, this is from another paper of Tim's, that's showing that if you have this very porous material that's forming your planetesimal, thermal conduction is inefficient, you can keep the surface very cold and prevent melting. And so, yeah, this idea of having an unmelted crust and a melted interior, I think, is a really neat way of producing bodies that could deliver water to Earth. So with that, thank you so much. I'll highlight that Liam's looking for a postdoc next year, so please reach out to him if you have opportunities or ideas for him. And I want to also thank my collaborators and funding sources. So thank you.
Thank you very much, Megan. Thank you so much for this very nice talk. And I clapped for everyone in the room because it's always awkward on Zoom. Also, thank you for specifically actually for highlighting these additional ideas, which I think we didn't have in the last session. So that's very great. And I'm absolutely certain that there are many questions now. So we'll see how this goes. So has anyone questions for Megan? Ah, very good. We have the first. Amy, please.
I'm very happy to start. Firstly, thank you, Megan, for a really cool talk. I very much enjoyed it. I wanted to ask you about the ability of the CC reservoir to deliver water. Do we have any constraints on how many bodies in that reservoir, like what fraction of bodies in that reservoir were melted compared to were not from the
yeah. So to the extent that our meteorite record samples everything uniformly, which is a big question, then I mean, we can use the abundances of iron meteorites from that reservoir as an estimate. I'm not sure I don't remember the numbers offhand, I'm afraid. Okay. It's interesting that the crustal and mantle portions of those bodies are so poorly preserved, and we only typically get to see the cores. So yeah, there's definitely some issues with preservation of samples and like what gets into our meteorite record, and that make that kind of analysis a bit tricky. But I think first order, we can use the abundance of iron meteorites with a carbonaceous signature.
Okay, thank you.
Yeah. Sorry.
I have more questions, Tim, if no one else is keen.
Yeah, let's give it maybe 5 seconds. I'm sure there must be more questions. There were many different topics, you know, considered. So like, I'm sure someone else has a question here.
Or if anyone else can remember the relative abundance of carbonaceous iron meteorites, please pitch in.
All right, let me switch. Actually, I have a question about your sample preparation. So for the so for this glass, I forgot the name. So is this an artificial material as well? Yeah, the glass you basically compare.
Supercell. Mm-hmm.
Okay, and how? So this is yeah. Okay, so this is prepared, and the water is artificially inserted into this material. Yeah.
Well, they actually, I think, want it as dry as possible. So,
but they measure it afterwards, and it typically contains on average 2 ppm or something like this.
That's right. Yeah.
Okay.
So they make huge vats of this stuff. I think it's for fiber optic cables and things, and they want it to be dry so that it has the right properties for their industrial applications. And we just use it because it has this uniform, very low water content.
Okay. Any other questions from someone else than the moderators?
Hi, I'll ask a question. I'm not sure if you can hear me. Okay. Hi, thanks. I really liked that talk. Also, I'm Claire from Cambridge. I think my name is not my full name. Sorry. And maybe this is not your expertise exactly, or maybe someone else can answer this, but I'm wondering if there's an isotope signature in gassing nebular hydrogen as a way of getting water, or not.
Yeah, absolutely. Yeah, the nebular gas is thought to be very poor in deuterium, very poor in 15 nitrogen, 14 nitrogen. And so the signature of nebular ingassing would be a very low DH ratio and a very low 15 nitrogen over 14 nitrogen ratio.
Right. Is that going to be overridden by eventual atmospheric escape or something else? Or is it like a useful constraint? I guess that's what I'm getting at.
I think we lost you, Meg. Cannot hear you. Can anyone else hear Megan?
Oh no.
Oh, now you're back. You're back.
I'm back. Okay. Yeah. So yeah, it's very complex. A lot of processing can mess up that signature. And one model that's been put forward is that that the nebula's gas is only around for a few million years, and they think that some of it could have partitioned into the core, the water from that reservoir. And that would disturb the isotopic composition by kind of hiding that contribution in the Earth. But there are other studies coming out that are constantly looking for these negative DH ratios. There's one just published about the achondrites and lodronites that found a slightly negative DH ratio for that parent body that could potentially be a nebular signature. So yeah, we're looking for that signature all the time in the meteorites. On the Earth, you're right, it's very complicated because of atmospheric loss, because of loss to the core. Yeah. Thanks.
We have a question by Rob Spargar.
Thanks. Hi, I'm Rob from ETH. Really nice talk.
Hi.
I would actually like to continue on what we were just talking about, because if the nebula has a different isotopic signature than both the NC and the CC reservoirs, then rather than a 2-component system, we should talk about a 3-component system, right? Well, in literature and also for most of your talk, I'm just hearing this 2-component system between the NC and the CC reservoirs.
Yeah, so in terms of the rocky bodies, then we can talk about the dichotomy. In terms of the origin of water, that we're talking about comets, nebula gas, which aren't these rocky bodies. There we have potentially 3 components. We've got very light isotopic nebula gas, we've got heavy isotopic cometary material, and we have the rocky bodies and the terrestrial planets in the middle there. And I don't know if you remember, I showed a picture of mixing lines between those reservoirs that are very strongly curved. So people do definitely consider mixing in different amounts of the nebula, the comet, and the rocky body reservoirs. But it's difficult to account for Earth's volatile budget by mixing in significant amounts of nebula gas or comets, just because the mixing lines are so strongly curved that they take you quite a long way away from the Earth. But it's possible, certainly, to mix in some amount of those reservoirs and not disturb that system too much.
Question by Hannah Sanderson.
Hi, I'm PhD in Oxford. I was just wondering, I was interested in what you said. You did the nanosim sampling of the endocytes to look at the water from the augrites, to look at the water from the Piani result. I was wondering how you chose, like, where in the augrites to sample. Did you look at specific minerals, or did you look within a certain area? How can you say that there's definitely not any water in there?
So this is a great question. Yeah, they're almost entirely anstatite, but we also have small amounts of sulfides and metals and some other phases. So what Liam did is he analyzed the enstatite. He had to be very careful to avoid contamination, so he used this real-time imaging on the nanosims to make sure he wasn't including any kind of contaminated areas. And then he got the 10 ppm upper bound on the enstatite, He then looked at modal mineral proportions for the metals, the silicates, and all of the other phases. And he has done the kind of mass balance calculation of all of those different phases to get an upper bound on the Albright parent body water content, which is still very, very low. So there are major uncertainties in how much water can partition into metals and sulfides, but the fractions of those phases are so tiny that even within the uncertainties, it gives us a pretty robust upper bound. His papers should be out soon, I hope, in EPSL. It's in review. Yeah.
Great. I'll keep an eye out for it. Thanks.
Do we have any more questions? If not, I have actually a controversial question.
Okay.
So on your very last slide, it's the very last point, you said that, and I think we discussed this, but for the sake of everyone, I just shortly we discussed this already, a bit controversially, but I want to bring it up again here. So in your, like, not actually on the conclusion slide here, the very last point was something like, yeah, CC signature does not necessarily indicate water-rich material. So what if we turn this around? Does it mean, can we turn this around and actually say an NC signature does not necessarily indicate water-poor material or not?
Yeah, to a certain extent, like we have bodies within that NC reservoir, like the ordinary chondrites and the achondrites, that have some water, that have sufficient water to explain Earth's water budget. The difficulty is making all the isotopes work at the same time. So the nice thing about the carbonaceous chondrites is that they have so much water, like up to 28% water by mass, some of them, that you have to add such a tiny amount to explain Earth's water budget that it doesn't disrupt the other isotopes in terms of building the Earth and making everything fit. So it's a little more difficult to do that with things like ordinary chondrites that are isotopically, they're NC, but they're still different to the Earth, and they have a lower water content than the carbonaceous chondrites. This is the attraction of the enstatite chondrites, right? That they perfectly match the Earth in terms of all of their volatiles. And so we don't have to worry about messing up our isotopic systems by accreting more and more enstatite chondrites. But their water budget in general is kind of lower, but potentially, like I think the bulk measurements, it would be good to support them with in situ measurements of the enstatite chondrites, and to support that upper bound on their water content. But they're still a perfectly promising and viable avenue, I think. Yeah.
All right, thank you. Okay, Amy, you had a question very early on. Did you have? Is it still valid?
It does. Megan, I was just wondering about what happens when the meteorites arrive onto Earth and how much volatiles are lost during that process.
Yeah. How
will we know actually how?
Yeah, it's been very, very difficult, I think, to tease that out. So particularly for things like carbonaceous chondrites, they're full of phyllosilicates and things that are very easily altered. So there are a few things we can do to kind of minimize that. If you observe a fall rather than like finding something a long time after it fell on the Earth, then you can minimize the terrestrial contribution. But we always have risk of contamination. Our sample return missions that are happening, these Hayabusa missions that are directly sampling asteroids that are potentially the kind of parent bodies of carbonaceous chondrites. I mean, that is the ultimate in like pristine sample, and that's so fantastic that stuff's happening. And then in terms of like historically how people have tried to do this with carbonaceous chondrites, they can look at the fraction of matrix material versus the other like chondrules and things, and the carbon and water contents, they correlate with the fraction of matrix material. So you can also begin to work out, like by teasing out the fraction of organics as well, and looking at isotopic correlations with the relative abundances of organics and phyllosilicates, you can start to constrain the water isotopic compositions and abundances of the different kinds of M members that combine to form the chondrites. So you can constrain things like the DH ratio of the water from the organics and the DH ratio of the water that was probably accreted as ice when the chondrites formed. And you can see those combining together along a mixing line. So approaches like that are really helpful for trying to tease out what is, like, there are definitely primary signatures in there. It's not all contamination. Yeah, but it's certainly tricky.
Okay, thanks.
Okay, I think let me ask one last question. Then if no one else has a question, we should stop. We should not unnecessarily extend this question. But so when you're talking about pH all the time, so I attend many astronomy conferences, and in astronomy specifically with regards an astrochemical, communities, the thinking goes that much of the water that we have on Earth is inherited from the molecular cloud because of a perceived match of the DH with measurements in the most pristine samples, comets and things like this, in star forming regions essentially. So I wanted to hear your general thoughts, musings on this, if we can construct such a direct one-to-one relation between pristine formed water in interstellar clouds that makes it really to a fully fledged planet. Do you think this is something that could potentially work, or will it be reset so many times during planet formation and melting of planetesimals? I think Joanna Gita wants to say something. I would be happy if she could comment on this. Yes. Okay, don't know. Maybe
sorry, Tim. I actually had a different question, a really dumb question.
So sorry.
Nothing as brilliant as yours. So please go ahead.
Too bad. I really would wanted to hear your take on this, but okay. Megan, what do you want to say on this?
I'm not sure. So there are definitely like chemical reactions and exchanges that happen in the nebula, like between water ice and other phases. I know we think that there's a gradient in DH across the nebula. I'm not sure specifically how to answer your question, Tim. I mean, I've definitely heard chemists, talking about interstellar water being important as well. But I don't know that I have much to add. Yeah, sorry.
Oh, that's fine. All right. Yeah, Joanna Gita, please.
Thanks. And thanks, Megan, for a really amazing talk. It was, there's so many things that I didn't expect to hear. And so of course, this is totally outside my area of expertise or anything. So maybe these are really dumb questions, but it seems really maybe surprising that everything is so dry. Does that say something, or what does that say about how these materials lose their water? I guess since some of the other measurements had measured so much more water and everybody was comfortable with that, I guess there must have been some ideas about how they could have retained so much water, but then you show that there's so much less. What does that say about how they lose their water? Is that surprising? Is it well known how you can end up so dry?
Well, I think there's a lot of heating and melting going along in the early histories of these bodies. So I think it's maybe not too difficult to imagine how these things dry out, but I think it's interesting that you mentioned some of the other studies that have detected water. So they were analyzing slightly different materials. There are certainly some achondrites that do have slightly higher abundances of water. And one thing that I Oh, let me see if I can find the relevant backup slide. So you can add some water to achondrites, potentially if like the kind of picture I'm building up in my head of how this works is that you have planetesimals that are very early formed, and most of them dry out very efficiently. You accrete to form a relatively like a planetary embryo that is probably quite dry, but you continue to accrete material. As the time goes by, more and more of that material is water rich, and as the parent body gets bigger, it's more and more able to retain some of that water. So I think the water can be added just at a slightly later stage of accretion. That's the model that I prefer. And that can explain the fact that bodies like Vesta and the anhydrite parent body have detectable water. And a study that I really like is a Seraphian study of the anhydrites that looked not just at water, but all of the volatiles, moderately volatiles and refractory elements, and showed that the anhydrites have elevated water and some moderately volatile elements that can be explained by addition of around 1%, I think, of carbonaceous chondrite material to a very dry precursor. So I like this idea that you dry out very efficiently first, and then there's this massive influx of wet material, and a lot of these achondrite parent bodies get small deliveries of potentially carbonaceous chondrite material quite later in their accretion histories.
Yeah, that's great. So in the context of the picture of Tim's that you presented, your first of the 3 end stories, I guess that suggests that the formation of these bodies has to preserve a relatively large mass of these small objects, rather than, like, for example, with the streaming instability for planetesimal formation, which immediately goes to pretty big objects, more than 20 kilometers, say. That you may be ruling that out as a very likely scenario?
Sure, or we can just accrete those dry and then add some of this later material that remains wet at the end, after a couple of million years.
Right. Okay. So that you can build these big objects, but they can't be 100% efficient. I don't know how much you need, how much of these smaller objects need to be preserved, that don't go into large planetesimals. So that's pretty interesting to consider, I think, for formation scenarios.
And if you are accreting carbonaceous chondrite to explain your water budget, remember you only need 1 or 2% to explain the whole thing. So the volatiles can be added very late and still account for Earth's water.
Okay, thanks.
No worries.
Okay, we can have the last question by Mark Elowitz. I want to shortly finish the live stream so that we don't run at the top of the hour. So thank you, everyone.